let's continue with one more example. Example number 4. And by now, I hope you already master how to draw shear and moment diagram. Now this example is a little bit more complicated. But just combine those we just learned from the first 3 examples previously. So you have a beam, and we have a pins at the left, and we have a roller not on the right, but here, that side, and the distance between that point so you see 4 feet, 6 feet, and 5 feet. And we have the load at 4 feet from the lab. It is 10 kips. And then we have a distributed load, so it's a little bit complicated with multiple load, concentrated load, distributed load. And in the worksheet, you have even the couple on this beam, for example. So from that here, I assume this one is 2 kips per foot. 2 kips per foot. So find out the external reactions. And you see, for your practice, I'm not going to write down here, but use your static and check with this. Okay, check with that. You will find out that if you take moment about the lab point A, okay, we put point A here, and we put point here. If you take moment about A, then you can find out the external reaction. Check yourself, because that's very important. I see that many people do in the exam, in the homework for the shear and moment diagram, it's the wrong start at the external reaction. So you will find out it's 16.5 kips at B, and then sum up all the force in the y direction. You can find out the reaction at A, vertically 3.5 kips. And if you are not sure, I want you to check another. You sum up all the force in Y to find out A, and then you check, make sure you correct. Take moment about B to find out either also 3.5 kips. If both way you get the same answer, then you're good to go to draw to find out to go ahead to draw the diagram. Bottom line, this is the last example, and I remind you, very important, find out the external reaction correctly. Multiple way, double check, otherwise it will correct in the shear and moment diagram. So with that, we can, and with that, practice this problem. Try multiple way to find out the external reaction at A and B. So with the shear, we can have here, and we have that one left there. At any point that have chain, then you put down the line, so that for sure. And similarly, we also have the moment diagram. So you also have here, and you can have that line and continue with that line. So we have shear V, and in this case it keeps, and we have moment, and in that case it will be foot kips. And we have positive, negative, positive, negative. So So from that, let's start with the shear diagram. It always start with shear and always start with the left. So from left, it always start with 0. So yeah, many always keep that in mind. Always start from left, always start with the 0, always start with the shear diagram. So here, and then up there. So 3.5 keeps going up, so create the discontinuity in the shear, move up 3.5. So plot 3.5 keeps. Between 8 to 10 keeps, nothing, so you will have the same 3.5. And then 10 keeps going down, so it causes a discontinuity in the shear diagram. Move down 10, so 3.5, move down here to 0, that is 3.5. You need another 6.5 to make that is 10 keeps. So you have move down 6.5, negative 6.5. So 3.5 positive, negative 6.5. That change in the discontinuity, 10 keeps, as you can see there. From 10 keeps to roller B, nothing. So it will be the shear, it will be horizontal slope 0. But the slope of the shear equal to the magnitude of the distributed load between 10 keeps and B, no distributed load. So slope equal to 0. W equals 0, distributed 0. Then slope of the shear diagram equals 0, horizontal, right? And then 16.5 keeps go up at B. It will cause a discontinuity in the shear diagram and move up. So that's 6.5. So you go up to here, that already 6.5, and another 10 to make a 16. So that point here, it will be plus 10. Because 6.5 negative plus 10, it becomes 16.5, and go up the chain there. And then the change in shear from B to that point, to the right point, equal to the area under to the distributed load. And you can see the area under the distributed load here, 2 times 5, so you will have 25. 2 times 5, sorry, it will be 10, and it's negative because the load going down, 10 in there. So the change in the shear from B to the right, it will be equal to the area under the distributed load, that is negative 10. So you have it plus 10, negative 10, so it will be stop at 0. And nothing else, so as you can see, finish at 0. On-way finish at 0 that you have in there. Make sense? And slope of the shear diagram there, as you can see now, equal to 2 kips per foot. That is 2 kips per foot. So it's straight line. Now go back to put the what line we are talking about, that is S, this is S, and this is S, straight line. And now go to the moment. When you draw the moment diagram, look at the shear diagram and find out the areas under the load, the shear curve. So you see 3.5 for the from 8 to 10 kips, 3.5 times 4. So you have 3.5 times 4. So each area is positive because the shear positive 14 foot kips. And then from 10 kips to the roller B, that is 6 feet apart, and the shear equal to negative 6.5. So 6 times negative 6.5, it equal to negative 39 foot kips. And then the areas here is triangles for the from roller to the right side of the beam. That triangle equal to 10, the base, and then the height equal to 5 feet. And that 5 times 10 divided by 2, that keep in mind, not 5 times 10 equal to 50. Triangles, you have to divide by 2. I see many people make that mistake. Not 50, but here it's 25. Keep that in mind. Everyone see that? Because that is triangle. So 10 times 5, 50 divided by 2. Because that's the area of the triangle, not the rectangles that you have 50 in that triangles. So from that, we can go ahead to draw the moment diagram. Moment diagram on way again from left, start with 0, as you can see. And then the change in moment equal to the area under the shear curve. Area under the shear curve from 8 to 10 kips equal to 14. So you will move here 14. And the slope of the moment equal to the magnitude of V. V is 3.5. The slope here is constant. So 3.5 kips. Go back to here. It will be the 14 foot kips. 14 foot kip. Everyone see that? And then from, and it makes sense. There are no distributed load in that portion, so it will be straight line in moment, right? Straight line. Similarly, no distributed load from 10 kips to roller B, so it will be straight line again. The change in moment equal to the area under the shear curve. The area under the shear curve from 10 kips to the roller B equal to negative 39 from 14 going down, right? Because that change negative, so 14 have to go down to negative 25 to be 39. And it's straight line. So that is negative 25 because 14 going down, negative 25. The total change for the moment from 10 kips float 4 feet to 6 to 10 feet from the left, it equal to 39 negative. So 14 negative 25 is 39. And then the last one. From the roller B to the rightmost of the beam, that the change in moment equal to the area under the shear curve plus 25. So as you can see here, 25 negative plus 25. So that one have to be 0, because that change negative 25 plus 25 equal to 0. That good. We are on the right track. And now the slope of the shear is non-zero and constant. In that case, slope of the shear diagram in this case equal to 2 kips per foot. At the matter of fact, that either distributed load is uniformly 3 kips per foot between the roller and the rightmost of the beam. So it has to be parabola on the moment diagram. And the bottom line, how can I draw the parabola? Can it be can I write this parabola? Something that I write in previously, just like here. Can I write that? Something like here? Or have to be like this. Which one? Think about yourself before I make a decision here. Can you tell me which one should be the moment diagram in the segment 5 feet between the roller beam and the rightmost of the beam? The blue or the black line? Both are parabola. To see that, you need to look at the shear, right? At this point, at the roller, the shear just about right of the roller, it plus 10. So the slope of the moment diagram at there is not 0. It have to be 10. And then, as you can see, the shear at the rightmost is 0. Then the slope of the moment diagram. At that point, had to be 0. Slope 0, it means that the line will be the tangential line to that moment diagram curve, moment curve, had to be horizontal. So with that, as you can see, you only have that ways, because that slope here is equal to tangential to the curve, and that one, it will be 0 at the rightmost. So that will be the curve that you draw, and it will be parabola here, and this is straight line, and you have, so bottom line, as you can see, uniform distributed load, the shear will be changed. It will be parabola in moment. In the worksheet, you also have the distributed load is not uniformly, but it's like a triangles. Then it will be parabola in the shear diagram, and it will be cubic in the moment diagram. You will see that in the worksheet. So keep that in mind. So with that, we're done for the lesson, and let's practice the worksheet. By now, I expect you to be able to do all of the worksheets without seeing the video of the worksheet solution.